while people are thinking of questions to ask, it's fitting to remember that Apollo 15 landed on the moon 49 years ago today. Nice little fact delivered by my colleague Jeff Gillis Davis.
This is Carly. I have a quick question I'd like someone to answer. The concept of trenching is really important, as many have pointed out. How, given the lighting condition with the sun, say a degree above, are you going to be able to see into the trench? If so, how far? What kind of orientation are you going to have to plan for to get the kind of data you'd like? I don't have the answer. I hope someone does.
This is Brett. I think one great way to get around having to worry too much about the lighting would be to do illumination with multispectral LEDs to get your kind of context imaging and help select the samples.
Absolutely agree. We can't assume we have the same environment as we had during Apollo's, but now we have new tools. Good example.
Yeah, this is Mike Siebert. We are actively looking at incorporating illumination into the sampler payload and future lunar robotics arms to do wide area and end effector level illumination, which could be very useful for the trenching.
Good.
Yeah, this is Clive. One thing that I haven't heard, and of course I may have missed it. We've been talking a lot about, trenching and samples and the different types of samples. But let's have a dose of reality here. What's the return sample mass? And I'm not talking about containers. What are the requirements for returning the mass of samples in the HLS and Orion, so on and so forth? So we know what the requirements are, and that may temper some of our discussions in terms of how we move forward with this. But right now I haven't heard anybody state what the requirements are for getting the samples back.
So this is Julie. I mentioned that maybe a little bit buried in my presentation this morning, but the HLS requirement is between 35 and 100 kilograms total down mass. So that includes the sample containers, that includes not just geologic samples, but other types of samples as well. And so, one of the things we're working on is trying to minimize the mass of the containers and, other hardware so that maximizes the proportion of that 35 to 100 kilograms that is actual geologic samples. So hopefully that helps.
So less than Apollo 17 brought back is basically what we're saying, which is a bit of a downer.
Well, Julie,
but I understand. We haven't done that in about 49 years this year, or 48 years this year.
What's the number that's being passed around, Julie? Is it between 40 and 50 kilograms?
So actually, the HLS designs are at the higher end, and the designs have not been finalized, but they are not at the low end. So I think we'll be closer to the in terms of geologic samples, I think we're hoping for on the order of 70 plus kilograms. So
okay.
We don't have specific numbers yet. Just want to be clear about that.
Well, it's certainly a lot more than was returned last year from the moon. So by human missions. So again, I think this is. I got to take my Apollo perspective hat off and say, this is going to be good no matter what. But I think we need to keep this in the back of our mind in terms of the systems that are being developed that will then enable our science. And so we've talked about the sample containers, but that's all part of the return mass. And is that going to inhibit actual samples coming back? So a cryogenic sample return is going to require quite a massive sample container. So
Right.
we need to keep that in perspective.
Yes, and that's part of the reason we're doing the NASA at Work and crowdsourcing challenges to understand what the state of the art is in terms of cryogenic cooling. And so we've actually provided some notional requirements to industry and to NASA internal cryogenics experts to provide some hardware recommendations that are low mass and hypothetically low power to try to offset some of that sample return mass impact from having a cooling system. But yes, that's an absolutely good point.
There was a question, if I might, there was a question for Brett in the Q&A, and it might be worth just asking another question. The question is about how wide is the Tycho Ray at Shackleton Crater? Another question, and her answer was it's diffuse, but from the low resolution data, it probably covers a good fraction of the region between Shoemaker and Digalash. So very interesting. How does the distance from Tycho compare to the distance to Apollo 17? And do you know, Brett, if anybody has mapped secondaries thought to be part of that ray?
Well, we've started working on mapping out secondaries and have been collecting some really beautiful oblique images to work from. I'm not sure of the distance. I believe it's closer to Tycho, but the ray is clearly more distinctly visible in the reflectance data at the South Pole as compared to at Apollo 17, where it's quite difficult to make it out apart from mapping the secondaries. Was there more to that question?
No, I think that's it. Thanks. Pretty exciting, though, to think that somewhere in the regolith there are some pieces of ejecta from Tycho.
Yeah. There you'd be much more likely, I think, to find direct, like Apollo 12 Copernicus ropey glass kind of material, since you can actually see the ray itself.
Oh, we're still looking for that material in the Apollo 17 samples too.
Yeah, this is Jack. That was my question. If anybody's ever identified it, there is the crater cluster on the floor of the valley at Taurus Retro does have an unusual, faint, remote sensing signature that's different than the surroundings. But I'm not. That could come from any number of sources, but I'm not aware of anyone finding Tycho ray material at Taurus Retro.
Right, Jack. There have been some candidates, but none have proven in the long term to be, definitive or the right thing. So we're still looking.
And now the hypothesis is that, and now alternative hypothesis for the avalanche, the two avalanches, is that it's fault-induced, moonquake-induced rather than Tycho-induced.
Yeah, and so if you visited a ray at the South Pole, that'd be, another clue to how that light mantle was produced. If you can kind of date Tycho at the South Pole, you can get a better idea on how the light mantle ties into the whole story.
This is Julie. I had a quick question for Laz about some of the ISRU components of things. You mentioned in one of your slides the scale of ISRU operations and how regolith needs to be characterized on that scale. Can you talk a little bit more about what that scale could be and maybe what frequency of samples would facilitate ISRU operations over that scale?
So I would presume it would be a scale of roughly 100 meters by 100 meters for, early on. There's obviously desires to work with much larger areas. And that's why the last thing was on the number of samples. With 10 samples, you can start to calculate a standard deviation. So you get some sense of the uncertainties or the variability. But it's about 30 samples before you get a good sense of what the distribution really looks like. Does that mean 30 good cores, or well, the other question is how deep are you going to go? Early on, you're probably not going to be digging very deep, so the push cores will be plenty good. And then there's the question of how much risk you're willing to take, trying to do ISRU on a deposit you haven't well characterized. You could consider the early attempts at doing ISRU to be more experimental, and therefore you're going to derive the information as you try to dig it up. So I don't know if that answers your question, but those are my thoughts.
No, that's great. Thank you.